recording this session, and so let's see. People are coming in. 34 people. We should be more than this, hopefully, but let's see. Okay, so if you recall, last time we have started the discussion on dynamic allocation of memory for, let's say, keeping data of any type, and we used malloc to allocate a single memory block for our data, whatever that data is. And we said also that if we need an array of, let's say, entries, meaning a number of memory blocks instead of a single block, then we will use what is called a calloc function. And while malloc actually required only one argument, the size of the block in bytes, calloc actually requires two arguments. One is the size of the individual memory blocks. One of those, a single block, how many in bytes a single block would require. And then the second argument, actually the first argument in this case, is going to be the number of elements that will be required by you. So if you need, let's say, an array of 10 entries of, let's say, simply, if you need an array of, let's say you have some type, let's say my type, and you want to have 10 entries, an array of 10 entries of this type, then you would send this one as with a sign, let's say size of, right, as a second argument to malloc, the calloc, sorry, and 10 as the first argument. This will be the calling of calloc function. So 10 is the number of entries or number of elements, and the second argument is how many bytes is required for a single entry. So this would return to a pointer, and you would keep this pointer in a pointer variable of the type that is actually defined here. So this returns what we call a typeless pointer, a void pointer. So what you would do is you would cast these two things that you want. So this is in this case my type, and you will cast it to my type pointer and keep it in a pointer variable so that that address is not lost. So you can use that address. Okay, so we have seen examples of malloc the other time. Calloc is similar. So there is an example here. For example, what we have is we have this planet T type, and I want to have an array of these. So I want to keep that array in a pointer variable. The name of the variable is array of planets. And the way that I would actually, in this case, what is happening is that the program is reading the number of entries, number of planets from the user, right? And then it will be using how many numbers, whatever the number of things that you are going to be actually required. And it will actually use calloc to get that number of, let's say in this case, what am I doing here? Let me see. This is, so you can actually read a string this way, an unknown string. So before we were doing something like this, we were saying str, let's say 50, We were assuming that this will be the maximum size. Instead, what you can do is you can say, okay, how long or how, let's say, big a string do you want? And then you can read that size, and then you can actually dynamically allocate it. The same for the number of, let's say, numbers, a set of numbers that you want to read from the user. You can ask the user, how many numbers do you want? Or perhaps if this is in a file or in a line, you can read that line or file and figure out how many entries in that file or in that line, and then allocate the right amount of entries for your array. And this is going to be done always with calloc. And calloc's first argument is the number of entries in that array. The second argument is in bytes, how many bytes that will be required to keep a single entry of that array, right? And this is the casting to the right type, pointer type, and this is the variable, pointer variable, that actually keeps that address in so that you can use it for whatever purposes that you want to use it for. So here, after this, I can use this array of planets. This is now is actually this is a pointer, and since I actually define it to be multiple entries using calloc, I can access this thing by as if it is an array using these square brackets, and entry, whatever entry I want to actually access, whichever entry. Of course, this index here, or that number, cannot be more than the number of entries that actually I defined. So if I have non-planets, let's say 10, this cannot be, it has to be less than 10, 0 to 10. So the same thing applies as before, as if this is an array, but it is just actually now a new way of creating an array. Instead of doing array this way, I am actually now on the fly deciding what the size of that array should be. Okay, so this is an simple thing. So when we look at actually what happens during the runtime, so let's say at line here, let's see, let's erase this clutter. So the first allocation actually happens here, and this is for the string 1. The string 1 is actually defined here as a pointer at line 7. Now I cannot access string 1 with anything, either this way or just as a pointer. I cannot access the where it is pointing at. There is no way that I can access it. Why? Because it hasn't been allocated. It's not allocated yet. When is it allocated? It is allocated at line number 13, where I use a calloc and I ask the user how many characters he wants to enter, and I read that character number of characters, right? So this is the definition. This is the number of characters. This is the number of bytes for each character, which is 1. I use a calloc, it will return me now a memory. This will be, so this is the pointer variable in my function data area, or what we call stack. And within the heap, calloc returns me an entry, an array of however many. So in this case, apparently this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we have to be, of course, careful here. If the user says, I want to actually enter 5 characters, then you would probably do a +1 here, because there will be 1 more character needed at the very end for keeping the end of string indicator, right? So if the user says, I want to type, for example, my name, Jakub, it actually has, let's say, 5 characters in it. If I'm asked to actually enter my name and ask how many characters in my name is in my name. I will say, okay, 5. Therefore, your calloc will actually allocate 6-character long array because the last character will be a null character to indicate the end of string, right? So now in the second one, the second array that I have here is this guy here. This is an integer array. It is intended to be an integer array. It could be actually just a pointer, or it could be an array, depending on what I do next. What I do next here is I'm using calloc to actually allocate some number of entries of integer type. Therefore, here, this will be now treated as an array. And in this case, apparently, I actually allocated 5 entries, 5 blocks for each integer entry. And similarly, I have here another pointer defined as or declared as planet T type. And at some point in the code, I have to initialize it. This is where I initialize that. And this initialization actually is a calloc. This means that I am actually gonna be returning an array pointer to an array in the heap. And the length of the array is actually the non-planets, and the size of each entry is gonna be size of planet T. Therefore, I will have here, in this case, I have apparently, let me see, 1 and 2 entries. So I use calloc with first argument 2, second argument is however many bytes that is actually needed here, which is defined by the size of. And now this guy is an array of planets is an array. Why? Because calloc is used. This can be taught, I could have actually, let's say if I use here malloc somewhere for, let's say array 1 or array of numbers, this guy, for example, with a malloc, then it will be actually either a single entry or an array with only 1 entry, right? I can treat malloc as either as a single entry or an array with only 1 entry. So if I had, for example, let's say here, somewhere a code like this, let's say double x, pointer x, and at some point in the code, I say, okay, this is double, let's say, pointer, malloc, and size of double, and so forth. So if this is the case, what will happen is that malloc is going to give me only 1 place in the heap just to hold 1 entry of type double, right? This will be the pointer. I can actually use this as like this with a star x indicating that I want to actually refer to whatever is x is holding, which is an address. I'm gonna refer to the value at that address. This is one possibility. The other possibility is also this one. This is doing the same thing. If you recall, this is saying that I want to treat x as an array. I know that it is not actually an array, but anything with one size entry can be thought of as an array of only 1 entry, right? It's the same thing. So this is the same use. So this and this is the same thing. Either I say star x or I say x within square brackets 0. So if I actually do here, let's say x1, then I have a problem. Why? Because x is actually referring to or pointing at heap where only 1 entry has been allocated, not 2, not 3, not 4, only 1. Therefore, you cannot access the second entry here. Now, of course, the funny thing is, or what we need to be careful here is that since C doesn't know how many entries you allocated at runtime, this will be defined at runtime. C cannot check if you are doing this indirection or indexing right. So in the code, I could easily have x1 like this, and C wouldn't know about it. C wouldn't say, okay, this is wrong. But because C cannot decide at compile time, the compiler cannot decide at compile time if this is wrong. This will be only happening at runtime. And at the runtime, what will happen is that you are going to say, okay, this is the X, and you are going to be trying to actually access here, which is supposed to be another one, but it is not allocated. So since this space is not allocated for you, this will probably cause a segmentation fault or some sort of a memory access fault. It will be error, right? Okay. Now, if this malloc and calloc is helping us allocate memory at runtime, what happens if we don't want to use that memory anymore? I needed at some point in my code at runtime, I needed some memory. Let's say I needed an integer array of 10 entries. I allocated it. I did my stuff with it. I calculated something. Now I no longer need it. I don't want to keep it anymore. Why? Because I don't need it. I am done. This was a temporary need. Now, keeping this in there, meaning keeping this memory still intact, and while I don't need that memory, is a waste of resources for what you are going to be doing, right? So you have resources. One of the most important resource that you have during the programming is, of course, the memory. And if you are, let's say, creating some intermediate, some temporary stuff in the heap, and once you are done with it, you should be able to somehow tell the compiler that, or tell the runtime engine that you don't need it anymore. You don't want to use it anymore, so that it can be used for something else as needed, right? So for that one, when you are done with the memory that you allocated, you can return the memory back to the memory manager. This is what we call a memory manager. So you say, okay, the compiler, let's say, assume that compiler is doing this on the at runtime, this memory management. You say, okay, hey, memory manager, I don't need this memory anymore. So I did a malloc at some point. I did my stuff with it. I'm done with it now, and I want to actually give it back so that that memory allocated for that purpose can be reused later on for something else. So this is called, there is a function for that, and the function is simply called free. Free takes an argument, and this argument is supposed to be a valid pointer. Valid pointers means, hopefully, it is actually obtained from a call to a malloc or a calloc function. Okay, so either of those will actually give you a valid pointer into the heap, and you would actually take your pointer and send as an argument to this free function, and free will actually now free that thing from that num, in this case, num pointer, right? So you would no longer have that memory available to you. So you can do this for multiple entries, of course. Now, what happens though is that once you free it, the thing is that free function tells the memory manager, okay, I don't need this thing anymore, so take it away. You can reuse it if you want to, if there is a need, right? For example, I can do, let's say, a malloc for something, and then I can actually, so let's save this in X, and I can do, let's say, another malloc for Y. I'm ignoring the casting here, and then I can free, for example, X, and then later on, for example, I can do another malloc for let's say Z, in this case, perhaps the space that is actually allocated for X earlier now is reallocated for Z, for this use of Z in Z's place, right? This is important. So when we say free, we are giving it up and we are promising that we are never going to actually touch that memory anymore. Now, what this function doesn't do is it doesn't actually change the numpy or array of planets pointer. Whatever the pointer is actually currently having, the address is still there. So in principle, once I actually do a free, and let's say that, assume that at the malloc, numpy is, let's say, the address is, let's say, 0011FF, let's say. This is the address that was actually returned to me after the malloc. When I do a free, now the address in heap for this place is going to be gone. So it is going to be actually returned to the memory manager. All right. Now, later on, I still have, after this free function, I still have the numpy variable, pointer variable, is still holding this number here, this address. So I can, in principle, do something like this, equals, for example, 0. Now, if I do this one, this is a problem because now numpy is actually holding this address, but I gave up on that address already. It is gone. Now what I'm trying to do is I'm trying to store something on that address. I'm trying to store 0 there, but this is not available to me anymore. So this is most likely is going to cause a problem, a memory access problem for me. So usually what we assume is that after this thing done, we would actually do something like this. We will say numpy is no longer this number, because this number is gone after the free. So I would probably do something like this. There is a defined name that is called null. This is also called null pointer. So what I will say is that, okay, numpy variable now is pointing at null, so that later on, if I try to actually access it, I'm not going to try to access this one. I'm going to try to access the 0 end address, which is going to be also a problem anyway, but at least it's not going to be this problem, right? So free function doesn't change the entry of numpy. It doesn't change it. So therefore, what you need to do is you need to be careful when you actually, or later on, what you do with the variable numpy. You should never ever use it before you do another perhaps assignment to it. And that assignment could be either a malloc or calloc, or it could be, let's say, an address of a existing variable. So it has to be reinitialized. If you don't reinitialize it, then you will cause problems. And here I am reinitializing it to be null so that I can check later on if this is null, I'm not going to actually do anything with it. So this is kind of a safety check for me to know that numpy is no longer in use. All right. We kind of forgot to mention the malloc and calloc returns an address. Okay. Now, what if there is not enough memory for your required call to calloc, for example? That means that, let's say that heap is exhausted, meaning heap is full. There is no more memory in heap. Your program consumed them all in the during runtime. So when the heap is full, or there is not enough space in heap for you to allocate whatever you requested, then malloc or calloc will return you something indicating that the address is not valid. Therefore, it actually didn't succeed. And the way that it will return you is it will return a null pointer to you. So if it is unsuccessful in allocating, dynamically allocating that memory from the heap, malloc or calloc function will return you null pointer. So what we usually do is, once we, let's say if we do a calloc like this here, let's say, where do I have it here? So if I do a calloc or malloc like this, I would actually check after this statement, after line 13, I will check if this string1 pointer variable has a 0 entry or not, or a null entry. If it has a null entry, I say, okay, calloc did not succeed. Calloc was unsuccessful. If it has a non-zero entry, then it must be the way that we actually, or calloc guarantees that if it is 0, it failed to allocate the memory. If it is not 0, then it actually successfully allocated the memory for you. All right. Is how malloc and actually calloc works. So for example, here I have an example. This is, I have 2 pointer variables, xp and xcopyp. All right. So I actually use malloc to create a single entry, okay, cast it and put it in xp. So in heap, I allocate this guy and then put the address inside xp, variable xp. So if the address here, for example, let's say, as I said, maybe let's say CSE102, let's say like this, then xp is gonna hold this address. And when I actually do, for example, star xp, it says, go and look at where this xp is pointing at, where this address is pointing at. And then there has to be, since you use malloc to get that address, there has to be proper amount of memory there to hold my double variable in this case. So hold this, it can hold this number 49.5. So this assignment is gonna actually load this number into that heap, into that space. So store it there. Now, here what I'm doing is I'm doing another thing. I'm saying, okay, let's actually take this XP, which is an address, again, FFCC1100, right? And copy that address into the other variable, other pointer variable, xcopyp. Can I do that? Yes, because they are actually both same type of pointer. They are double pointers. All right, good. Then what I can do now is actually, I can say, for example, after this line, forget about the last 2 lines. If I say, let's say, xcopy p equals 11.0, for example, what will happen is that since xcopy is pointing to the same place, this indirection will mean that I'm going to actually put 11.0 on this space, in this space. So I will replace 49.5 with 11.0. So I could have done the same thing with xp. xp and xcopyp will do the same thing. Now, one thing that I have to be careful, this is what we call aliasing. So we aliased the same memory space in heap with 2 pointer variables, one this guy and another this one. So there are 2 pointer variables pointing to the same address space, right? So now if I go and actually do a free operation, I say, okay, free XP, the compiler or the runtime engine is going to say, okay, this guy doesn't need this one anymore, so it will free this one. Now this means that this is no longer valid. So this is no longer valid. Even though it's not going to change the value, XP's value, I know that since I do this one, I usually do something like this afterwards. I say, okay, this is null. Now XP is pointing to 0. I know that I will check if it is pointing to 0, I'm going to say, okay, don't use it. But if I do this one, I still think that, I may think that, I know that it is not the case here, but I may think that since I am actually pointing to the same place, X copy P may not know that XP has been actually whatever XP is pointing has been freed. It is returned to the memory manager. So this will cause a problem because this thing is no longer available to my use here because I freed it here in this line. So even though this looks like you cannot catch this problem though at the compile time. At compile time, this looks fine, right? But at runtime, this will cause a problem because XP, wherever the XP is pointing at, which is also pointed by X copy P, they will be pointing to the same place. But since the first one actually used to free it, the second one may not know that it is actually freed. So if I try to do something like this here, then I have a problem. This is very, very dangerous. So you have to be very careful when you, especially alias, create an alias of your, let's say, pointer address somewhere. So if you make multiple copies of your address that is returned by your malloc or calloc, you have to keep track of them and make sure that when you free one of them, when you free that memory space, you update all your copies properly so that the other copies don't try to access to same place, that place which is actually already gone or already freed. So this is a kind of a common mistake or common, let's say, semantic error when we use actually multiple pointers to a single cell. So you may ask, why would I do such a thing? We'll see that this is going to be actually quite useful to have multiple pointers to, let's say, to the memory that is created at, or the memory created in heap. Why? There will be algorithms that we are going to see later on that will use this convenience of actually C. So those references, these addresses, can be manipulated easily to actually for a dynamically created, let's say, cell in the heap. But with that flexibility comes a cost. The cost is you have to be very, very careful. If you are not careful, you can actually cause a lot of problems. And one of the problems is this freeing an alias or multiple pointers to a single cell. And when you do free one of them through one pointer, the other pointer should be made aware that that thing has been actually freed. So this is an important thing. We are going to see this one later on. Okay. So any questions so far? Any questions? Let me see. You're not reading my instructions here, guys. I said your name, number, and a tilde sign. And some of you don't have a tilde sign. Number, just a tilde sign. Okay, anyway. Questions, let me see. Free func, what is this? Okay, so he responded to my, I guess, rhetorical question. Okay, so he says, Bahadır is asking, oh, okay, Mustafa is asking, malloc and calloc arasındaki fark var mı? Of course, right? So the question is there any difference between malloc and calloc? Yes. When I use malloc, I am actually allocating just one entry for example, if I'm doing malloc for a double, I will be creating a cell for only one double number. Calloc will actually give me an option to create more than one. So, for example, let's see. If I use let's say in this case, I said malloc double, right? I could actually, this is again for one entry. If I want to actually do, let's say, I want to have not just one entry, but an array of entries. Let's say, for example, I want to have, let's say, 3 entries here. Not just one entry, but 3 entries. In that case, I will use calloc. And the second argument is going to be the same as the first argument here, the size of one entry, and then 3 here. So this 3 is going to say, okay, I need 3 of them, 3 double numbers. I want to keep 3 double numbers. That means that now XP0 is the first number, this one. XP1 is the second number, and XP2 is the third number here. All right, good. Or we have seen this one earlier, or we can say XP this is the same as XP0, right? And let's see, let's erase some of these. So XP star XP and XP0 points at the same place. All right, this is good. And for example, XP plus 1 and star points at exactly XP1. And star XP point 2, we discussed this one last week if you recall, points to XP2. This says take your pointer value, the address, increment it by 2. When you do the increment by 2, compiler looks at what you have in XP. What is an XP? XP is a pointer. What type of a pointer is this? It's a double pointer. So in terms of addresses in bytes, when you increase a double pointer by 2, you mean actually to go from the first one, from first one to second one, and the third one. So you go two entries down or 2 entries later, next 2 entries, right? So this is the value of this one is going to be in bytes, in as an integer number, is going to be actually increased by not by 2, but by 2 times 8. 8 being the number of bytes required per double number, right? And which is the same as this guy here. Okay. Now going back to who was a question from? Let's see. Going back to question from Mustafa. Now he was asking, calloc and malloc are the same? No, they are not the same. As you can see here, malloc actually gives you only 1 entry. Calloc can give me more than 1 entries. So in this case, it gave me 3 entries. I cannot use, in principle, malloc to actually give me the same thing as what calloc is doing here. But there is a trick here. So the trick is this one. So for example, I can use calloc like this. Size of double. Why not? So I'm saying just give me 1 entry. These 2 are the same. Using malloc size of double and calloc 1 size of double is the same thing. Okay. So in principle, they are not the same thing, because if they were the same thing, C wouldn't have 1 of them. The economy of, let's say this is the kind of economy of choice here, that you don't want to have multiple things doing the same thing. That's ridiculous. Why do you have those type of things, right? So calloc is doing multiple allocations. Malloc is doing 1 allocation. All right, but here I used calloc as if it is a calloc. So I actually only got 1 entry. So in this use, they are the same. Sometimes you can also do this way. So let's say that if you use 3 here, now they are not the same. The first one is actually doing on the 1 entry, creating on the 1 entry, space for 1 cell, whereas the second one, calloc, is doing 3 cells, one after another. So continuous block of 3 cells. Now what you can do is you can actually go here and say, okay, 3 times size of double. Now this says I want to have memory in my, let's say, in my heap allocated. What is the size of that memory? I'm saying, okay, the size of double is 8 bytes times 3. I want 24 bytes. Now, this is saying, okay, I'm going to actually get 24 bytes continuous in the memory. This is saying. This one does the same thing. It says, okay, get me 8 bytes, first 8 bytes, and then another 8 bytes, and another 8 bytes, and one after another. So in principle, what happens in the background is these two things are actually doing the same thing, right? In principle. But semantically, even though they actually lead to the same thing, the intended use of malloc and calloc is against the use here. Malloc says, please give me the number of bytes that you will require to keep a single entry, and I will actually do it for you. And calloc says, give me that number as well as however many number of blocks that you want to have of that same size. So the semantics of these functions are different. Their intended use is different. Even though you can, since they're at the end, they are actually allocating memory for you, you can trick them to actually give you the same thing. But it doesn't mean that you can either of them, one of them instead of the other. The proper use is, if you are doing a single entry, use malloc. If you are doing an array of entries, use calloc, because they are designed for that purpose, right? So Murat's question has an answer. In principle, no, they are not the same thing. However, since C is kind of a very flexible language, you can use them. Again, technically you can use them instead of the other one, but you shouldn't, because the semantic is, even though the end outcome is going to be the same, the semantics intended to actually to be created by this thing, the outcome that should be created by these two things, are supposed to be different. Therefore, technically you can use them instead of the other, but in practice and to be true to the language's design purposes, you shouldn't. All right. And there was another question. Let's say free pointer ile pointer'ın tamamen aynı mı? No. Bahadur is asking free pointer. Free pointer will free the pointer. It's not going to set the pointer variable to anything, right? The other one is just saying, let's look at it this way. Let's see. So if I had, let's say, this one here, let's say, instead of this one, I had xp equals null or assign null. So what will this do? This will just actually break this link, and then this says, okay, now I am pointing to 0 here. What happened to this guy? It's still there. It didn't change. So this one, this assignment to this one, is only changing what I keep, what address I keep in that pointer. It doesn't change the fact that the previous address that I kept there has been really allocated in heap, and it is still there. It's not going to change. So this function, though, what happens is that it will remove, or it will release, the address that is kept in XP. That address is actually is referring to a cell in the heap, and that cell is going to be freed. All right. So they are certainly not the same thing. All right. Let's see. And there is another question. Hocam bir kere free yaptığımız hafızayı bir defa kullanamıyor muyuz? So if I can interpret this in two different ways, this question. So if I free this thing, for for example, let's go back to the original code here. If I free this thing, this is now gone, right? So XP and X copy P is pointing to not existing thing, something that doesn't exist anymore. Okay, this is the first thing. This is important. All right. Now, when I actually, if I try to do, for example, this one, memory is no longer mine. Someone's microphone is on. I'm hearing your voice, and please mute it. It's kind of distracting us. So this is not gonna work because this memory is no longer mine. I cannot access it. So if your question is this, once you free something, the address is still in your hands. Having the address to that freed place doesn't give you the right to actually use it. It's not available to you anymore. Even though you have the address, it's like this. I mean, you rent a house from someone, you rent an apartment, right? And then you live in that apartment for 1 year, and then you just, let's say, vacate the apartment, and then you go to somewhere else, but you still have your address. Now, when you vacate the apartment, you are now no longer paying rent for it. It's no longer yours, even though you know the apartment, you know where it is. It doesn't mean that you can just go and actually get in that apartment, right? It's someone else's apartment now. So knowing the address or having the address to that memory place doesn't mean that it is yours. If you didn't do a free, it is yours. If you freed it, now it's not yours. You said, okay, you are leaving the apartment, and the landlord takes it and gives it to probably someone else, or it may be empty. It doesn't matter. After you actually exited the apartment, you are done. Here, once you free the memory for that particular address, it's gone. As I said, freeing that doesn't change the value in XP. The address is still in XP, or I have a copy of it in somewhere else. It doesn't mean anything that you can actually get into there anymore because it's not yours. You might have copied the key to the apartment, and your friend has one, you have one, and then you exited the apartment, you vacated it, and now it is maybe free or maybe it's occupied by someone else, and then you know that you are not actually going there anymore because you actually exited the apartment. You said you are no longer renting it. Your friend might have the key, and if you don't let him know that that apartment is no longer yours, then he may actually try to get into the apartment using his key. But having his key doesn't mean that he has the right to actually get to the apartment because you exited it. You actually vacated it. You are no longer paying rent for that apartment. All right. So I hope this is clear. Let me see. We have 2 more minutes before the break. So Atakan's question, once we freeze something, we cannot use the same address to go there. However, that memory can be actually used by another malloc or calloc later on. Whatever you freed, that space, can be used later by some other calloc or malloc operation. Is it guaranteed? No. It depends on the memory manager. It's like this. I have, let's say, as a landlord, I have three apartments in my building, and I am renting it out. You come to me and I rent the first floor to you, and another person comes and I rent the second floor, and then let's say a year later, the first let's say the first guy actually leaves the apartment. Now I have the apartment. I can rent it, let's say, for a newcomer, I can rent the 3rd floor or the 1st floor that you vacated, right? So it's up to the memory manager to actually reassign those blocks or memories to new malloc or calloc operations, all right? So you cannot guarantee that it's going to be used or it's not going to be used, but it can be used. All right, another question, let's see. Are there any questions? Yes. Malloc size of double number. So you are saying that here, this is the same as calloc, yes. So isn't calloc AB equal to malloc AB? Yes, this is the same thing, Ozan and Eren. And isn't the same as calloc? Yes. Is there any way to reactivate the pointer? Okay. Now, for the first three questions or comments, the answer is yes, they are the same. Technically, they are the same. But semantically, you shouldn't do it, because again, if that was the case, then the end effect could be the same, but the way that it is done can be different. It's not that different, but at least semantically, the compiler tells you use this one for this and then use this one for this one, because they mean two different in the code. When I see a calloc, I know that I have an array. When I see a malloc, I know that I have a single entry. If I actually do 10 times malloc or malloc 10 times something to create an array, I am cheating something, and this is not a good way to actually do. All right. Is there any way to reactivate the pointer? Not with the same area. So this is a good question. So I'm hoping that the question is something like this. So let's say that I actually did come here and I freed it. Now XP doesn't actually have even though XP has the address, but that address is no longer valid. Okay, I have the key to the apartment, but I don't have any more a contract to get into the apartment. I don't pay for it anymore. I just vacated the apartment, right? I just, let's say, changed my contract. I no longer have a contract to live in that apartment, but I have the key. So key doesn't mean that I have the access. Now the question is, can I hope to actually use the same key to get into the same apartment? You can say, okay, go to the landlord and say, okay, I want to re-rent the same floor, please, or same apartment in that building. This is not guaranteed. If I actually do XP equals another double, let's say this malloc and whatever here, this malloc and this malloc doesn't necessarily give the same address to me. It will not give the same address, most probably. So you cannot trust or you cannot expect it to give you the same address. So I think who was the question from? Where is it? So Eren is asking if this is, let's say, giving me the same address, perhaps now I can use this guy, the same alias. The answer is no. Malloc or calloc never guarantees to give you the same address. If you freeze something and then if you get again the same thing, you may or may not get the same address. There is no guarantee. So sometimes you may, sometimes you may not. Because memory manager can say, okay, or let's say as a landlord, when you come to me and say, okay, hey, I like that place in the first floor and I have the key already, can I rent it? I say, okay, maybe if it is empty and if I like you still, I may give you. Or I may say, oh, I have a better one in the third floor, take that one, or fifth floor, take that one. Because whatever is available, even though if it is empty, I may still not give it to you. Because my algorithm to actually judge you which apartment you should get in and which apartment I should give you is up to me, not to you. And there is no expectation that you can ask me, oh, I was living there, let me have that again. No, there is no way. Memory manager will never know this one. It's not designed for that purpose. It will give you whatever it thinks the best for you. And it may be the same thing or it may not be the same thing. And most probably it's not the same thing. Okay, let's take a break for 10 minutes and we'll be back. 10 minutes.